So now we take this equation, the general wave equation, and we put that value inside. So we input into that equation the value that we found for the speed of propagation of the wavefronts as time increases, or the wavefront of constant c. And the velocity of propagation along normals is, for a fixed energy, so let's input that into the equation to describe the wave function of the electron. V squared is equal to E squared. So remember that E is a fixed stationary energy. We'll define stationary later on if we have the chance. So the equation is now Schrodinger made an assumption, which is that we know that the energy of an electron is given by its frequency. So we know that the Planck's constant times, well, assuming that the wave of the electron takes this form, and assuming that this phase takes the form of we can try first to determine the value of C. So we know that H, Planck's constant times the frequency, is equal to the energy. Since that part is given by 2 pi f, we have that energy over C equals 2 pi f, and we know that energy is equal to Planck's constant times the frequency. So then C is equal to h over 2 pi, which we just call h bar. This is Planck's constant, and this is Planck's constant divided by 2 pi. So we know now we would have that this is given by that, the stationary solutions. That's what he assumed. And since it's given by you'll have that if you take the time derivatives, it will simply give the same function, but with I times minus E H. So that taking a second time derivative would give and this is just E squared H bar squared and I times I. So when you plug that value inside that equation, you have canceling both sides, rearranging, you find to rearrange you would have we can write that as the Laplacian. Can divide by minus 2m. And we have that energy is equal to it's not that, this is a, it's commonly written that way simply so here you have it, you have the Schrodinger equation for fixed stationary energy. And so this applies to any kind of particle, not only electrons. So it's more general, but if you were to have an equation for the electron, the mass would be equal to the mass of the electron and the potential would be equal to this. So, but if you have a sum of different stationary energy, then you will find that the sums of these energies, if you were to add them with constants, they will obey separately, they will obey this equation. But for the whole sum to obey the equation, you would want that part to be replaced by. So we have that, we had earlier that this is equal to energy, so you have that energy times the wave function is equal to h d phi, it's equal to I h bar, the Schrodinger equation for time-dependent solutions. So each of these is given by an independent, time-independent amplitude. and you will have that the phases, the time phases will be equal to this is just this here plus yeah, there is a I here. This is the one energy, this is another stationary energy. And so when you take a sum of two different stationary energies, you will find that the amplitude will depend on time. So it's not, the solution is not stable. There will be fluctuations of the amplitude. So what is interesting is that Schrodinger found that this operator, the Hamiltonian operator, he found that this operator allows solution such that it will obey the property that if at a certain time that times its if you took the inner product of that function at a certain time, then at a later time, you will find that is also equal to C. So we could interpret that quantity as a probability density. So you will find that this over a certain region, we can give the condition that it's equal to 1. So then if you took the integral in a certain region of space, you would interpret that as a probability to find the particle in that region. This is because for this to be equal to 1, you just need to take that integral and divide it by C to normalize it. And the fact that the total integral stays the same over time is because the operator, either the time derivative or that operator, is a self-adjoint operator. But this is beyond the scope of that video. We just wanted to prove the wave function. So that's it, I guess.